In this problem, we're analyzing the work and power of an electric motor. An electric motor exerts a constant torque of 10 newtons times meters on a grindstone mounted on the shaft. The moment of inertia on the grindstone is 2.0 kilograms times meters squared. If the system starts from rest, find the work done by the motor in 8 seconds and the kinetic energy at the end of this time. What was the average power delivered by the motor? Okay, so now we can start writing down the values that we already know and that were given to us. We know that the torque was 10 newtons per meter, and then we know that the inertia is a 2.0 kilograms times meter squared. And then lastly, we know that the time that we're being asked to find is 8 seconds. So now, we're being asked to find the average power delivered by the motor, and we're also being asked to find the work done and the kinetic energy at the end of the 8 seconds. So we're going to need a few equations for this, and first off we need the work equation, which will be the torque times the change in delta. And then, the change in theta. And then to find the torque, we have to do the inertia times alpha. And then to find this, we would have to get the torque over the inertia. And then we already know these values, so we know that the torque is 10 newtons times the meters, and we know that the inertia is 2.0 kilograms times the meter squared. So this value that we're looking for here, we already know that it is 5.0 radians per second squared, and that is our angular acceleration in this case. And then we're being asked to find where the work is done by the motor at the end of the 8 seconds. So now we would have to get theta, and then we'd use this equation of theta initial plus the work initial times t plus half times t squared. So the change in theta is going to be half. Since we know that this is 0, it's just going to, and we know that this is also 0, it's just going to be half times the 5.0 radians that we found times the 8 seconds squared. And this leaves us with 160 radians, and this is going to be the change in theta, the change in the angle. And now to find the average power delivered by the motor, we have to find this other equation. So we have the work, and we know that the work is going to be the torque times the change in theta. And we already have both those values, so we would just take the 10 newtons times meters, and then for the change in theta, we now know that it's 160 radians. So the work that's done by the motor in 8 seconds is 1,600 joules. And now lastly, to find the average power delivered by the motor, to find power, we would do the work over the change in time. And we know that the work now is 1,600 joules, and the change in time is 8 minus 0, so 8 seconds. So it would leave us with 200 of the work. That's the power, the average power delivered by the motor. And then here we have the work, and then here we have the kinetic energy at the end of this time.